All right, welcome back. So let us just revisit what we discussed in the previous lecture. What we discussed was this, that for any experiment, let's say you are making some observations. This is your experiment, and you are making some observations in the experiment. You can also call it data. These observations are assumed to come from a true generative process. So there is some truth behind these observations. So let's say you are observing whether people are able to recognize words correctly or not. When you show them a word, let's say book on a screen, whether they recognize it or not, right? So that's your observation. But there must be some true underlying cognitive process in human mind that is generating these observations. Now the goal of statistical inference is to know what is that true generative process. And it's very difficult because you cannot know. So what is that exactly true generative process? Only way you can know something about this true generative process is using the data. So whatever data you have collected. So which is called statistical inference. So using the observations, we make some inference about the true generative process. But how do we do this? What is this process of inference? Well, the way we do it is like this, that we make a fundamental assumption about this true generative process. What we assume is that this true generative process must be a probability assigner function. This is a function, remember? So probability assigner function. This function can have different forms. So that depends on your assumption, what you assume. Okay. So for example, you can assume that this true generative process is a function f of theta, or you can also assume this is a function g of phi. So you can assume different functions as well, right? So it's your assumption, what you assume about this true generative process. So you make some assumption about the true generative process. And what is this assumption? That this is a probability assigner function with some properties, right? So here we have assumed this probability assigner function is f with the parameter or argument theta, and here we have assumed it's a probability assigner function g with the parameter phi. Right? What this probability assigner function does, it assigns real values to events in your event space. So you can think of event space, possible events that can occur in your experiment. This probability assigner function assigns real values to events in your event space. But this real value assignment is not arbitrary. It is constrained by certain restrictions called 3 axioms of probability. Okay. So that's how we define probability. That probability is a way of assigning real values to event in your event space constrained by certain axioms. Okay. That is probability. So it's a more like a function, right? So it's a function which gives you some real values for the events in your event space constrained by certain axioms. Okay. Now what is inference? Then how do we make inference? So this is the assumption part. So for any inference, first thing you need to do is to make assumptions. And what kind of assumptions we make? We assume a probability assigner function. Okay. This is not a proper mathematical name, but we will rethink of what exactly we should call this probability assigner function. It has more technical names, but this works for us for now. Okay. So this is the kind of assumption we make. We assume a probability assigner function which would assign probabilities to events in our event space. And this should be a reasonable assumption. This should be a good assumption. Otherwise, this whole inference thing wouldn't work. So it's very important that you make right set of assumptions. Okay. And you can also realize by now that you have degrees of freedom in making this assumption, because you are making assumption, right? Someone else can make a different assumption. Someone else can say that these observations are not generated by f of theta, but they are generated by g of phi. So you can make different assumptions. Okay. But this is a very fundamental part of inference, that you need to make some assumptions. What assumption you make, that's up to you. or that may depend on the theory or the opponents in the field. So, that can depend on different factors, right, but you need to make some assumptions for inference. And what is the assumption? It's a probability assigner function. So, what is the exactly the probability assigner function that might have generated these observations? Now, the second thing you need to do to make inference is that using these observations, infer the properties of your probability assigner function. So, for example, using your data from the experiment, infer what value of parameter theta in f, right. So, what value of theta would have generated these observations under the assumption that these observations were generated by this function f. Okay. So, basically what we are doing here is that using your observations, based on your observations, you try to infer or you try to estimate exactly what probability assigner function might have generated these observations. Okay. And by extension, you are trying to infer what is the true generative process behind these observations, right. But there is a problem here, you can see, which is this, that, well, you don't know whether you have made right set of assumptions, right, that you would never know whether your assumptions are correct or not. Okay. So, the inference would always remain incomplete if you basically try to infer the true generative process using only one assumption without any competing assumption, right. So, if based on your data you have inferred what is this function, exactly this function f, and you try to make a claim that the true generative process is f of theta hat or something, then that would remain incomplete, okay, because this holds true only under the assumption that observations were generated by this function f. Okay. So, to make inference complete, you always need to compare whether f of theta is better than some competing assumptions, let us say g of phi. Okay. And that is the only kind of inference you can make, that whether the assumptions you have made are better than some other competing assumptions. That is it, because you cannot know absolute truth whether f of theta is the true or right correct generative process. You can only say whether f of theta is better at explaining these observations compared to g of phi. Okay. So, that is the second thing you do, that based on your data you try to infer the exact process f of theta or g of phi, and then you try to compare to competing assumptions. Okay. So, basically you compare f of theta and g of phi to see that which one is a better set of assumption. We will go into more nuances of this, what exactly it means to do the second part, to make inferences about f of theta and g of phi. But for now, this is the workflow of inference, statistical inference, that you first make assumptions, okay, about that what is the underlying probability assigner function which is assigning probabilities to events in an event space. Then you try to infer the properties, exact properties of that probability assigner function using your data, and then you compare competing probability assigner functions, competing assumptions, to infer that which one is better at explaining the data. Whatever is better, you would think that is closer to the true generative process, right. Now, what we need to understand is that what are these three axioms, three restrictions on probability assignment, because that would define what is the nature of these probability assigner functions. And second, what kind of assumptions you can make exactly. So, what is exactly the nature of f, what kind of function f you can assume, what kind of function g you can assume, right. So, we will see what a realistic probability assigner function may look like. Okay. So, just to revisit on three axioms. Okay. So, we discussed three axioms in the previous lecture, just to make you revisit them. So, the first axiom was this, that for any event E which belongs to your event space F, probability of event E should be greater than equal to 0. So, that was the first axiom. So, you cannot assign non-negative probabilities. Second axiom was this, that one of the elementary events must occur. So, if E1, E2, E3 if these are elementary events, okay, such that E1 union E2 union E3. So, if they are elementary events, their union would be basically your sample space. Right? So, for elementary events, E1, E2, E3, if these are elementary events, one of the elementary events must occur. So, what you can say is that probability of E1 union E2 union E3 is equal to 1. Okay. So, probability of the union of the elementary events is equal to 1. Okay. Third axiom says that if events E1, E2, E3, En are mutually exclusive, two events EI and EJ are mutually exclusive if their intersection is an empty set phi. Okay. So, for mutually exclusive events, probability of their union is equal to summation of their individual probabilities. That is the third axiom. Okay. So, the second axiom says that one of the elementary events must occur. So, probability of the union of elementary events is equal to 1. Third axiom says that if two events are mutually exclusive, then the probability of their union is equal to summation of their individual probabilities. So, probability of E1 union E2 equals to probability of E1 plus probability of E2. Okay. And we saw that using these three axioms, we derived a result that, let us say, if these are the elementary events in your experiment, this is what we derived for an experiment where participant has to give a yes no response, right. If these are the elementary events, then the probability of E1 plus probability of E2 is equal to 1. So, this is something we derived from second and third axiom. Okay. Of course, probability of E1 and probability of E1 both should be greater than or equal to 0 here. It can't be negative. Okay. So, these three axioms would determine what would be the constraint on your probability assigner function. Okay. Now, let us take an example and let us see what a realistic probability assigner function might look like. So, we can revisit our example where participants see a string on a screen and their task is to recognize whether it is a meaningful word or not. So, they will respond with no if it is a non word, and they will respond with yes if it is a meaningful word. Okay. So, what is the sample space of the experiment? Sample space is a set containing yes and no, right. What is the event space? It is a set containing yes, no, yn and an empty set. Okay. So, this is your event space. Let us name these events E1, E2, E3. Okay. Now, first axiom would say that probability of E1 or probability of E2. Okay. So, all these probabilities would be greater than or equal to 0. Okay. So, probability of E1, so based on first axiom, probability of E2, okay, they would be greater than or equal to 0. What would second axiom say? Second axiom is about elementary events, remember. So, one of the elementary events must occur. So, that is probability of union of elementary events E1 union E2 should be equal to 1. That is the second axiom. What would third axiom say? That if two events are mutually exclusive, what are the mutually exclusive events here? E1 and E3 is not mutually exclusive, they have one common element y. E2 and E3 is also not mutually exclusive. Okay. So, the mutually exclusive events here are actually E1 and E2, which are also elementary events, by the way. So, if two events are mutually exclusive, okay, so here E1 and E2, then the probability of their union, so probability of union of two mutually exclusive events is equal to summation of their individual probabilities. Okay. Now, you can derive from equation 2 and 3. So, equation 2 says that E1 probability of E1 union E2 equals to 1, 3 says probability of E1 union E2 equals to probability of E1 plus probability of E2. You can derive from these two that probability of E1 plus probability of E2 equals to 1. What is E1? It's an elementary event containing only yes. What is E2? It's an elementary event containing only no. Okay, so summation of these probabilities is equal to 1. Okay, also from first axiom you know that probability of y and probability of n, okay, this should be greater than equal to 0. So whatever probability assigner function you would define, it should follow these restrictions, right? So let us think what probability assigner function you can define. So maybe we can start with a very naive and very simplistic probability assigner function. Okay, so let me define the function like this. I'm defining a function f of theta. Okay, so the function is f of theta. Okay, such that the function would have a value theta if let me write it more precisely so that it's not confusing anymore. So let's say the function I'm defining is f of w theta. Okay, I will explain what w is. Okay. So it's a function of two arguments, w and theta. So it would have a value theta if w is yes. Okay, or you can just say y. Okay. So if the outcome is yes, then the value will be theta. Or if the elementary event is yes, then value is theta. If elementary event is no, then the value is 1 minus theta. That's my probability assigner function. And why it works? What is w here? W is basically a member of your sample space. So I can just instead write them as y and n. Okay. So if w is y, this happens, and w is n, this happens, right? Where w is a member of your sample space. So this is a function I've defined. What this function would do, it would assign probability to these events y and n. How? So if you are talking about this event containing only one member y, okay. So let us see how it can assign probabilities. So if the event, or let's say w, is y, okay, then what is the value this function would have? Theta. And if w is n, the value this function would take would be 1 minus theta. Okay. So if we take their summation, it satisfies the property that probability of y plus probability of n is equal to 1. Okay. So that's the basic idea we are trying to follow here, right? All right. But what is theta? So you need to define theta as well, right? So we need some interpretation of theta. What is theta? So let's say theta is the probability of yes response. Okay. Underlying probability of producing a yes response. Let's say that's theta. Okay. So if the elementary event is yes, okay, then this function would have value theta. If it is no, the function would have value 1 minus theta, right? Now depending on what is the true underlying probability of yes response, this function would assign probability values. What does it mean? So let's say your cognitive process is such that, or let's say in a particular task, a participant is just making guesses, right? The participant is not even seeing what is the actual word, and they are just making random guesses. In that case, the true underlying probability of yes response would be, let's say 0.5. Okay. That means for an event where response is yes, the probability assigner function would assign. So, to event E1, the function would assign what probability? For w equals to y and theta equals to 0.5, right. So, these are the values arguments will take, right, for event E1, because it is event E1. So, w will have value y, w will be yes, and theta would be 0.5, because it is a gas process, that is why. So, it depends on the process, right. So, or the truth, right. So, true generative process. So, probability of E1 would become 0.5 and probability of E2 would become f of w equals to n and theta equals to 0.5. So, it would be this 1 minus 0.5 equals to 0.5. Okay. So, this is how this probability assigner function can assign probability values to the events in your event space. So, what it requires to assign probability values? Well, some information about the event to which you want to assign the probability value and some information about this parameter theta. So, this parameter theta is unknown. So, this is a parameter and very fundamental thing that we will later on see, that in most of this course we will be trying to estimate this parameter theta using the data, because we do not know what is this true parameter theta for any particular experiment. Okay. Why? So, think about it. So, let us say you are doing the you are doing this word recognition experiment, okay, on, and you are showing every time some non word like BKTR, and what you observe that you do this 10 trials, you do this experiment, let us say 10 times, and what happens is that 7 times you get a yes and 3 times you get a no. Okay. So, what could be the underlying process that could generate such data? Okay. So, even when we assume that the underlying process is this, the underlying probability assigner function is this, right, even then the value of theta would determine whether you can generate this kind of data or not. Okay. So, if theta is, let us say 0.2, then it is very unlikely that this process can generate this data. But if theta is, let us say around 0.7, then it is very likely that this process can generate this data. Okay. And that is very interesting, because now using the data you need to estimate, using this data you need to estimate what would be true value of theta for which this particular process can generate this data. Okay. So, for example, theta equals to 0.7 would be more likely than theta equals to 0.6. Theta equals to 0.6 would be less likely to generate this data compared to theta equals to 0.7. So, you can actually get basically a function that what values of theta are more likely to generate this data, what values of theta are less likely to generate this data. Okay, so, for example, 0.7 is most likely, 0.6 is less likely, 0.8 is less likely, 0.9 is very less likely, like that. This we will later see is called a likelihood function. Okay. So, this is how you can define a very simple probability assigner function. Now, what we need to think is that, well, this is a very naive and simple function which works for us for this example, but what if you have more complicated experiment where you have let us say 10 possible outcomes and then 10 possible elementary events. In that case, would you define a function containing 10 rows of these if else statements and then defining these probabilities theta 1, 1 minus theta 1 plus theta 2 and so on, right. So, it becomes very difficult as you go on to have more possible outcomes. We will see such examples in the next part. Okay. So, I will stop here and we will take some more examples in the next lecture. Thank you.